Good morning and welcome to the office hour recording for Tuesday, November the 8th, 2016. I'm Scott from Redmond Physics Tutoring and I'm growing a mustache for Movember. And I could just, if you go to http, actually it's just mobro.co/srphysics, you'll be able to see my fiddly attempt at how things are going. This is the first time I've tried. It's inspired by my kids because my daughter asked me to grow a beard this summer and it was way too hot in the summertime for me to do that, so I didn't. Anyway, right now I just started to set this up yesterday, and as you can see I have a fairly piddly little mustache going, but I'll have some fun with it. Anyway, I don't have anybody live right now, but I do have a question that I would like to look at. So let me start up Ink2Go. This was a question from one of my students. So I'll do a shout out to Alessa for bringing up this question. And it's actually from Waves and Optics and Modern Physics and talking about light waves. And the question was, actually, why don't I type it out here? The question was that, whoops, I have to be able to read my picture of it. Two waves of the same frequency have amplitudes 1.39 and 2.3. Oh, I can't do that. All right. Have amplitudes. Whoops, I want to go back here. This Ink2Go is pretty good, but not perfect, obviously. 1.39 and 2.38. They interfere at a point where their phase difference is 42.0 degrees. And the question is, what is the resultant amplitude? And so I'm a bit embarrassed because yesterday when this question came up during tutoring, I couldn't remember how to solve this. And it's because I really didn't get into phasors when I was teaching this course. To be honest, I taught this course 3 times, but in the same 2 semesters. It was kind of weird that way. And I didn't get a chance then later on, like with my other courses, I have had more time to I taught them in following semesters. And so each iteration, the course tends to get a bit better and a bit clearer. Anyway, in this case, I didn't actually look at phasors at all. So it turns out that the way to solve this is to use phasors. And before I describe phasors, I want to just really quickly, show you the Wikipedia page on phasors, because there are a couple of diagrams here that are helpful. So the basic idea, they have a phasor is a complex number representing a sinusoidal function whose amplitude, angular frequency, and initial phase are time invariant. Okay, that sounds really complicated. There's a more general concept called analytic representation. We don't need to know at the introductory physics level that it's a complex number. It's helpful to understand that the amplitude, angular frequency, and initial phase are related to the amplitude, angular frequency, and initial phase of a wave function. So where we have a wave function, and I'll add this here in blue, if we have a wave function as y, say at, I'm thinking of a transverse wave. So anyway, y as a function of x and t is equal to the amplitude times sine, and then we would have kx minus omega t plus the phase constant phi. That's the initial phase. Essentially, the phasor representation of this would be at a certain, say, fixed value of x. So x is equal to x naught. Then the angular frequency that I need to practice here. The angular frequency that they talk about here, omega, is the same angular frequency that we're talking about. The amplitude is the same amplitude that we're used to talking about. And the initial phase, Wikipedia is using theta, and in my classes, I'd always use phi. but it's the same as the phase constant, the initial phase. All right. Then just scrolling down a bit, the idea in this diagram to the top right, they're talking and showing how you would apply this for an electrical circuit, and I'm just not going to get into that right now. One representation of this is this nice GIF, animated GIF, that shows a vector rotating around counterclockwise, and that represents the phase. So the angle is the phase, represents the phasor. The amplitude of the vector, the length of the vector, corresponds to the amplitude of the wave. The phase of the vector is represented by the angle at which it goes around. So when it's all the way to the right, that's a phase of 0. When it's all the way to the left, that would be a phase of pi, and so on. And so what's nice about this graphic is that it actually shows you how that corresponds to the amplitude of the sinusoidal function as a function of y and t. The reason this comes up for this particular problem, remember, is that the problem says that we have two waves of the same frequency with different amplitudes, and they interfere at a point where the phase difference is 42 degrees. To find the resultant amplitude in the general case, we need to add their phasors. And if you remember, the phasors are vectors. And as vectors, they have a magnitude. So of phasors. So each phasor has a magnitude, and the magnitude, oops, that's magnitude, not magnitude. Is equal to I should rewrite this actually. The magnitude is equal to the magnitude of the wave, and the direction is equal to the phase of the wave. So if we represent this as, I'll say, wave 1, I'll draw in black, and wave 2, I'll draw in red. So then wave 1, we can just choose any arbitrary direction. So I'll choose just to the right, and actually I'll just define some axes off here to the left, x and y, that we typically have. And then the distance, or the length of this vector would be 1.39, and this would essentially be 1.39 I hat. Then for the next wave, it's actually going to be at an angle of 42 degrees from the first one. So I'm going to continue this as a dotted line just to give me a reference. But then I will draw this up, and actually it's longer, so I'll try to represent that. This angle inside is the 42 degrees. If I were not adding these up, in fact, I'll just add a page here. If I were just looking at these waves, and if I had my x and y axes, so I have a y-axis vertically and x-axis horizontally, then I could draw these, and I would have the first one going off to the right with a magnitude of 1.39. And I would just say the phase constant for the first one is equal to 0 degrees, or 0 radians, because 0 is 0. For the second one in red, the amplitude is going to be 2.38, so it's bigger. And the phase constant here, phi naught 2 for the second wave, would be 42.0 degrees. It could be negative 42, it doesn't really matter. These are two vectors as represented as phasors, where 0 degrees is along the x-axis, and then the phase increases counterclockwise from x. Then you go through 90, then 180, 270, and 360 degrees, or pi by 2, pi, 3 pi by 2, and then 2 pi in radians. So then I'm just going to go back. What I'm doing really is I'm just adding up the phasor for wave 1, which is down here in black, to the phasor for wave 2. And I'm just realizing I'm going to want some space there. So I'll draw this over here. Phasor for wave 2, which is in red. And I have to do vector addition. And I'm going to get a resultant that I'll draw in green. It's tricky to draw a straight line on this. But this is the resultant. So I'll call this, actually I'll just call this resultant R. And I'm doing vector addition, so I have to actually add these up. It turns out that 1.39 I hat for the first one is in unit vector notation already. The second one, I'm actually, for wave 2, I will need to break into x and y components to add this because my drawing is not to scale enough for me to sort this out. So this side on the bottom is going to be 2.38, which is the total magnitude, times cos of 42 degrees. And I actually didn't work that out. The vertical part is 2.38 times sine of 42 degrees. And then the amplitude, I just add these up. And the bottom part is going to be I hat, the vertical part would be j hat. To get the resultant amplitude, I totally cheated when I did this. Anyway, the resultant amplitude, so I take the amplitude of R and I can write that just with the arrowhead on top as a short form, is going to be V. Being picky about how neat this is. It's going to be the square root of the x, the sum in x squared. So I'll have my 1.39 plus 2.38 cos of 42 degrees. So that's the resultant x component squared, plus the resultant y component squared. So from the first vector, I have 0, plus, and then from the second vector, I have 2.38 sine of 42 degrees. And I take the square root of all of that. And then when I do that, in this particular case, I get 3.5374. And it just continues, but even on my, essentially at this point we're given 3 sig figs, so I would keep it at 3 sig figs. I always told my students to do what your chemistry teachers said about significant figures because I was more concerned about the actual physics thinking rather than the detailed math. And anyway, when you're given online problems like for web work or mastering physics and stuff like that, often they require more than 3 sig figs, especially for intermediate calculations, just for you to get an answer that the computer is expecting. So this is basically it. The idea of phasors again is that a phasor is a vector where the magnitude of the vector is equal to the magnitude of the wave, and the direction of the vector is equal to the phase of the wave. And the direction, again, if we have our xy axes, in terms of the direction, you measure the phase from counterclockwise from x. So 42 degrees was in the top right quadrant. If you had 200 degrees, it would actually be in the bottom left quadrant. And a 200 degree one would be pointing down, something like that. Then you just add them up, just like you add vectors. And in this case, we're acting as the question was asking for the resultant amplitude, and you just add up the x components, square them, add up the y components and square them, and then take the root of the sum of the squares to get the amplitude of the resultant wave. And that's it for this week. Feel free to tune in next week to see how my mustache is growing. And if you have a question, let me know. I would be pleased to answer it for you and help you out with physics. So good luck to you, and I hope to talk to you next week.